All right, there we go. See if this is a little better. Oh, look at that, phenomenal. Okay, so then we got work where we have an angle involved. Here's how you say this more compactly. You could say the same thing by saying work equals the force vector dotted with the displacement vector. That's called a vector dot product, and it means literally that. Okay. Later on in college calculus, you guys will, and in calculus-based physics in college, that's how you'll think of work. But for now, that works just as well. Okay, so let's kind of put all this stuff together here then. So we know what work is. We have a little more complicated or a little more complex definition of work. We know what kinetic energy is, right? 1/2 mv squared. And the work energy theorem. This is straight out of our book. It's equal to the change in kinetic energy, the work is. But we have to be a little more, this is all review. We have to be a little more particular about that because really, it's not just work, it's what we might call the net work, right? There's two ways to think about that. So you can think of it as being the net force, the single net force. Like if we take all the forces and resolve all the forces into one net force, like we've done so frequently, if we take that one net force times displacement times cosine of theta, that works. Or the other thing you could do is you could sum up all of the work due to the individual forces and add all those up. Because remember, work is not a vector quantity, right? It's just a number, which is nice. So we could add up, let's say there were 4 forces acting on an object. I could calculate the work due to each individual force and just add up all those works and get the same result, right? Either way, it's going to work. But it's the net work that's equal to the change in kinetic energy, not, so this really should say net. Okay, and that should, so that's what I really want to do. Complicated, okay. So work done by many forces. This just summarizes that a little bit, right? So we could either add up one net force or we could sum the work done by all each individual force. Okay? So that hopefully that rings a bell. That should all be fairly straightforward and self-explanatory. But now we got to get back to buying trucks. We're not quite through talking about how to buy trucks. Okay, there's two things we look at when we buy a truck. Color, torque, which we already talked about. What is torque again?
Force.
What is torque? Okay, so it's like it's the rotational equivalent of force. It's the twisting force, you might say, that the truck can produce against the road, right? So how much force can the truck, apply to the road? What is torque a good? What are you going to be probably using your truck for if you're buying a high torque truck? Probably pulling stuff.
Towing a boat.
Pulling stuff.
Towing a boat.
Okay, towing a boat. There you go. You gotta say that in an accent. Okay, so anyway, so the other thing we look at is what?
Fuel efficiency.
Very nice. That's what I like.
Yeah.
So I like. Okay. Yeah, there you go. Fuel efficiency. What's another thing you might look at if you're horsepower? There you go. You might be looking at horsepower. Okay, what is horsepower? Do you have any idea?
How many horses?
The amount of work a horse can do.
Okay, now that's originally what it was kind of supposed to correspond to was the amount of work that a horse could do in. I don't know. Well, it doesn't really matter because it's the amount of work a horse could do with time. The amount of power produced by a single horse. I don't believe that that's probably accurate, to be honest.
500.
There's no way. But okay, so power is equal to. Here's the definition of power. Power is the rate at which work is done, right? So it's work divided by time. So I want you to tell me here now, who's got a really, really is willing to admit to this, has a really crappy little tiny.
Oh, my mom's car.
Oh, that's
Yeah.
I thought he
had a
sidekick.
Sidekick. Okay. So let's just say that we reinforce the frame. Is it a 4-wheel drive?
Yes, well, it's a 4-wheel. I think you can ship it out.
Okay. So let's say we take Ian's Suzuki Sidekick, which I'm sure we all wish we could. We take this and we're going to hook it up to a trailer, reinforce the frame a little bit, put a big hitch on it. We're gonna hook this thing up to a great big horse trailer. Big horse trailer full of horses, and he's going to move this thing, he's gonna drive it up Cabbage Hill to the top. Okay.
Don't make it.
It's,
Put it
I mean,
down.
okay, if, it may not make it in, is it an automatic,
No, it's manual.
manual, 4-speed?
Yeah, no, 5-speed.
5-speed?
Yeah.
5-speed, okay, alright. So 5-speed Suzuki, there's no way it's gonna do it in 5th gear, probably won't even do it in 4th gear, but it would do it in 1st gear, for
Oh,
sure.
yeah. It's gonna take a little bit, but it can make it.
So we're gonna go up the hill in 1st gear, maybe taking occasional, it's cold weather, so it's making it up the hill. We get to the top and we park it at the, what's the Dead Man's, okay, park it at Dead Man's Pass, alright. So then we're gonna do, who's got just a Major League truck? Right here. So we're gonna hook up Brady's Major League truck here. And he's gonna, oh, by the way, your average speed was, 5 miles an hour going up the hill.
Let's push it.
That was push.
Push.
Yeah, Braden takes the horse trailer and he's going at 75 all the way up the hill, and he parks it at the top. Okay, who did more work?
They do the same amount of work.
They did the same amount of work.
Ooh, Kingo.
They did, right? They did the same amount of work because they took the same trailer to the top of the hill against gravity, right? Okay, which one exhibited more power in doing so?
Probably is.
Guessing not the same.
Not the sidekick, and here's why, because really what work is, it's just, it's the rate at which, power is the rate at which work is done, right? So, the same amount of work was done, but one of them was done in 10 minutes and one of them was done in 2 hours, right? One job. And so the power was very different. So then, power is really not, well, okay, it's useful, but it's maybe a little bit overrated in a way. If you're buying a truck, honestly, the thing you'd probably be more interested in would be torque, I would think. Okay. Although, I don't know, it's probably a little of both. Let's take a look at a couple implements here. So here's hold on one sec. Okay. Good, okay. All right, here we go. Okay, so let's have a look at these two fine pieces of machinery. Okay, you've got your agricultural tractor and sort of a sports car. Okay.
Yeah.
What do you think now? If I hook those things up with a tow rope and they start from rest, which one is going to win the tug of war? The tractor is going to win the tug of war so easily, right? Okay. Which one of those probably has the most horsepower?
The car.
Tractor.
Yeah, let's take a little vote because we're a democratic
Well,
society.
it depends on what you got in the tractor, because this tractor is like 100 horsepower.
Okay, it's that tractor has a big four-cylinder diesel engine, industrial grade.
Alright, so your car has more horsepower.
It's better if you already saw it.
Pretty close though, probably.
More torque in the tractor, but more horsepower in the truck.
That's what, actually, I looked this up today, and that tractor has 60 horsepower. That car has 467 horsepower.
Yeah.
Okay, why, what does the car do that requires it to have more horsepower?
This engine runs quicker.
Turbo
It does
fast.
fast.
It goes fast.
Right.
It goes
It
fast.
does
Yeah.
speed.
It can convert a lot of gas into a lot of energy pretty quickly, right?
A lot.
What does the tractor do that's so good? Well, the tractor, it doesn't do work very fast. The engine doesn't run at a very fast speed. It's not designed to, you're really not probably trying to show off by going real fast in that tractor. It puts along pretty slowly,
I don't know about you.
but you just can't stop it. I mean, it's really, it can pull with a lot of torque, right? Its job is to apply lots of force to the ground and move heavy things. You can put a blade on for it. It can do all that stuff, right? You can take one of those great big cats, those D9 cats that push around great amounts of earth. They don't have very many horsepower. I mean, it's like 100 horsepower. And yet you could just go right through a house with one of them without even slowing down. But this is different, right? What this is designed to do is the engine runs at a high speed. It doesn't produce a tremendous amount of torque, right? That's not the goal. Its goal is to be able to wind up the gear so you can gear up through many gears. And when you get to a high gear, you can still run that engine at a pretty high speed and still convert a lot of that chemical energy into kinetic energy, right? But they're different. They're different. I just want you to see that. All right, so let's look at a couple other things here. So then we started talking about this the other day. So mechanical advantage, actual mechanical advantage. You can either call it mechanical advantage or actual mechanical advantage. We said that this is really based on what happens to force, input force in this machine, right? It's just going to be the ratio of the resistance force divided by the effort force, right? So frequently with machines, what we most likely want to do, you can do either one, but most of the time, we're trying to multiply the force in such a way that we can do something that's otherwise impossible to do with just our hands or our human body, right? So that's the mechanical advantage, or the actual mechanical advantage. That is by measuring input and output forces, right? Resistance force is output force, effort force is input force. So we could also write this if we wanted to, like this. Okay, output over input. Okay, what about ideal mechanical advantage? Remember, that is, in a perfect world, what the mechanical advantage should be.
What's this?
What do we got?
Yeah, this tractor beat that car.
It's
100 horsepower tractor.
That's not a normal tractor.
Hold on, where's the point? These things.
Almost takes off as a wheelie.
Oh, Wi-Fi's.
Yeah, that's not normally what tractors do. Hold that up, bro. You gotta switch up that video. Yeah! That's all I do. Alright, that's probably filmed in, I don't know, where's that, probably filmed in Pile Rock.
It's in Sweden.
In Sweden. Oh, in Sweden. Huh. So ideal mechanical advantage, remember we said it's always based on the geometry of the situation, right? It's without any frictional forces, without any loss. This is what the mechanical advantage should be. Rarely is it actually accurate, right? Because there's typically going to be in some cases more than others, there's going to be some frictional losses. But this is based on the geometry. So it's going to be defined as effort distance over resistance distance. Or another way of saying that is effort distance going to be input or output distance? Input distance, right. So it's going to be the input distance over the output distance. And we're going to have to be able to interpret that differently for each simple machine, right?
So,
Yeah.
have we ever made something or like found a way to make like a lever or something that is 100% efficient?
You know, levers are pretty close to 100% efficient. Sometimes people call that a pure simple machine because there's really very little friction. I mean, if you think about it, if you're going to wedge something up, and that you do that all the time. I mean, what did I just do the other day? Well, I had to move something up, this big piece of concrete up onto my son's basket so it wouldn't blow down every day when the big wind comes by. And all you do, I mean, seriously, that kind of stuff, if you just get a 2x4 and you create a fulcrum, I mean, you can do an amazing amount of work or you can apply an amazing amount of force if you use a lever. Another thing I did, moved our dog kennel. Our dog kennel weighs like a jillion pounds. And without having to disassemble it, you can just kind of jack it up with a 2x4 and like move one end and move the other. I mean, really, if you apply the physics of simple machines, you can do amazing stuff. I mean, you really can do a lot of, you can apply a lot of force with seemingly very little input force.
Levers, probably the closest thing we have, you know.
Well, I'd say a lever's probably the closest thing we have, right? I mean, there really is almost no friction if you're just pivoting it on full. Yeah. Okay, so here's an example. Like if we look at, speaking of levers, what is this doing? If you open a bottle cap, you're applying, here's where the input force is being applied, but the output force is much bigger. It's, you know, you can't really just grab a bottle cap and pull it off, or at least I can't. Maybe Kate can, but I can't. Not with your fingers. Notice though that what you're trading here is you're trading distance. You're only moving the bottle cap just a little bit, right, Ian? And you can move your hand quite a bit, but that's all right. Who cares? It's a big deal. That doesn't really cost you anything precious to just to pull that bottle opener a little bit further, right? You'll give up that extra distance in this case for that very necessary increase in force, right?
Oh my god.
Okay.
Real company.
Movie day. Movie day. What are we talking about? So efficiency, we kind of ended up with efficiency yesterday, right? We defined it in two ways. We could say that efficiency is either equal to, we could say it's the output work divided by the input work. Or you could call that resistance work over effort work, right? And then if multiply by 100 if you want to turn it into a percentage, that's fine. Or we could say it's equal to the actual mechanical advantage divided by the ideal mechanical advantage. Either way, you're calculating the same thing. They're always going to be equivalent. Okay, and that's never going to be perfectly 100%, but it could get pretty close in some cases. All right. So what do we got here then? Let's look at the different kinds of, simple machines. Okay, so what do we call that, you suppose? You already know what that is. What is that?
Lever, fulcrum.
That's a lever. Okay. So what do you think now when we're calculating actual mechanical advantage is always easy to do, right? That's always just going to be what's the output force divided by the input force. Piece of cake, right? But what about the ideal mechanical advantages? Where are we going to count? We're going to have to identify for each of these different machines, we're going to have to identify what's the input distance and the output distance. So what's it going to be here for a lever?
It's going to be bigger than the output distance.
It is, but I mean, it's measured from where to where, geometrically. Like, we should be able to measure this and predict the mechanical advantage of that.
Fulcrum and then from effort.
How long the load arm is.
Okay, yeah, okay, good. Load arm and effort arm, right? We can say. So the input distance would just be the distance from the fulcrum to where the input force or the effort force is applied, right? And then the output distance would just be the distance to where the center of mass, in this case, of the load is, right?
Oh, it wouldn't be to
In
the
the
end of the
fulcrum.
arm.
Say it again?
It would be to the end of the arm.
No, it'd only be to where the load is being applied. Yeah, where the force is being applied.
So like, then the effort force would be wherever you push it.
Wherever you push it, right. So to get the most mechanical advantage, you'd of course push it at the end.
Yeah.
Right. Okay, make sense?
So you would take the measure of the whole effort force on.
Yep. Okay, and we'll look at each of these individually. Do you know what this is called? Pulley system or a block and tackle. Okay, what's that? No, it's not. It's a little different.
Crane. What is that? Looks like a crane.
This is, so now what's going on here is this outer rope is being wound around this wheel. It's got like a,
So that's like a gear down,
Is it?
It is.
Like,
it's called a wheel and axle is what it's called. So all a wheel and axle really is it's going to have one small radius and one big radius, and you're going to apply a force, an effort force to one of those two wheels, and the resistance force or the output force is gonna be generated by the other one. Now, it could go either way. You could either have a big mechanical advantage or you could have a mechanical disadvantage, for example, if you wanna get speed out of this, and we'll talk more about that later. So what's this right over here on the far left? D.
Slide.
Yeah, I mean, it's a ramp. Technically in physics, everybody know what we call that?
Incline.
An inclined plane is what we call that, but it's a ramp, same thing as a ramp.
Wedge.
It's a little different than a wedge. It's very strongly related to a wedge, but it's
Looks like a split.
well, it is now. So an inclined plane is the most simple form of a ramp, but then we can use an inclined plane. We can apply it in different ways. A wedge. This is what we call a wedge. A wedge is really just an example of two inclined planes that are stuck together, right? And where is the force applied on a wedge?
Blade.
Yeah, so we're pushing down on this thing, right? And then the wedge is applying the force outward, in this case to split the wood, right? Do you think that the efficiency is very high on a wedge?
There's tons of friction.
There's tons of friction. So the efficiency is very low, very low. What do you think? Okay, what is this?
Screws.
It's a screw, but what is a screw built from?
Metal.
Yeah.
Okay, but I mean, which of these do you think it?
Radial.
Spiral and incline.
That's what it is. It's just like an inclined plane that's been wrapped up around a solid spline, right? So if I were, does everybody see that? Like if you were to walk up this thing, this would look like a little ant were walking around this. It would make progress. It'd be like a spiral staircase, right? Well, what's a spiral staircase? Spiral staircase is just a big long staircase that's been wrapped around a central core to make it fit in a smaller area, right? But in principle, it's the same thing, right? So this is really just a wrapped up inclined plane, okay? You think the efficiency is very good typically for a screw?
Yes.
Very low.
Very low. Think what you're doing with a screw. When you're driving like a wood screw, you're having to move that thing against all that wood, so there's a ton of friction there, right? But what it does is it allows you to conveniently apply, you apply that twisting force with something like a drill or with a lever to multiply your force, right? And then you're able to do something convenient like pull wood together. Right? You can apply really large forces if you have a really long lever twisting that screw, right? Okay, and if you think about a screwdriver, if you're trying to drive in a screw by hand, would you rather have a screwdriver with a big thick handle on it or one that's real tiny handle?
Tiny.
No.
I would want a thick handle.
Because the tiny one, you wouldn't be able to, it'd be hard to twist, right?
Oh,
You
twisting
wanna
it.
It's
See what
like,
I'm saying?
just like your axle and whatever.
Right, like a wheel and
The
axle.
bigger the wheel.
Yeah, make sense? Okay, so then,
You gave me the
there's your key, all right. So what about then for something that is more complicated? This is what we call a compound machine,
It's a
right?
bike.
Where there's a lot,
Gears.
AKA a bike, yeah. Okay, in this case, a bike is an example of a compound machine. What do you suppose a compound machine must be?
Multiple
Parts.
different ones.
Yeah, a bunch of simple machines all put together, working in concert, right? And almost everything you use is really probably a compound machine. Very seldom you're gonna use just a pure simple machine, unless it's a fulcrum, a crowbar, or something like that. But on here, there's lots of stuff going on. What do you suppose that is?
The gear.
That's a
Okay, but the
What
crane,
is the
What's it gonna be?
Main axle.
okay, but which of those simple machines we talking about?
Pulley.
Or no, it'd be the wheel and
It'd be a wheel and axle.
Yeah.
Yeah, it'd be a wheel and axle. Now, really, the outer wheel, so what's the outer wheel gonna be? In this case, you're turning the wheel with a big radius. The pedal is really just an extension, it's just a piece of a wheel, isn't it? Right, when you turn a pedal, you're turning that pedal through a big circle. Very same as if you were turning it with your hands and it were a wheel, right? But you're just standing on one piece of it and moving it around. So that counts as, that the circular motion of that pedal counts as a wheel. And then you're going to turn a sprocket here that drives a chain. And if it's a multi-speed bike, then where you choose to put that chain, on which sprocket you put the chain, determines what the mechanical advantage of that first wheel and axle is going to be, right? Does that make sense? Okay, so you can kind of get an idea here. Now, we haven't gone into a lot of detail, but you can kind of get an idea how like a 20-speed bike would work, right? you're gonna be changing, by shifting gears, you're gonna be changing the radius. You're gonna be changing the radius of that, of the axle on that first wheel and axle, right? Because you're pushing on the wheel, which is the pedal, and you're turning the axle. Okay, so then, what about this mechanism here? You've got this chain that's binding both of those two sprockets, right? And so that's kind of like a pulley. Yeah, it's kind of like a pulley in the sense that you're transmitting force from one place to another, but really, the chain is just a vehicle for the force, right? The chain is just transmitting the force from here over to there, right? But then when you get to the back wheel, what's going on there? Let's focus on the back wheel. You've got this chain that's pulling on the sprocket. Okay, so you're gonna have a very small, much less than one, you're gonna have a mechanical disadvantage there, right? The chain is pushing on the sprocket, which has a pretty small radius. That's the wheel, because that's the part that's being driven by the input force, right? The output force is applied where? Yeah, to the road, right? So you get the whole radius of the tire is the radius of the affected axle on the back wheel. So what do you think you do then when you want to take this as one big compound machine? How are you going to calculate the overall mechanical advantage? You write it. Yes. That's how you apply it. How do you calculate it?
You have to find the gear ratio?
Yeah, you think you're going to multiply or
I
add
would add all those.
the mechanical advantages of the individual machines? It'd have to be multiplied, wouldn't it? Now, why
Yeah.
wouldn't if you just think about this without even focusing too hard on this exact specific situation? What's the biggest that a mechanical advantage? Well, nah, it's a bad way to think of it. Can somebody try to conceptualize here why you'd have to multiply instead of add? What if this mechanical advantage were 1 and that one were 1? Have you really, I mean, is the first machine producing any?
They're almost ratios, like.
If you added them together, you'd have mechanical advantage of 2, but since they both have mechanical advantage
Because
of 1, which really, if one isn't really a mechanical advantage.
Right, neither one of them by themselves is producing a mechanical advantage. All they're separated by this chain, which is just transmitting the force, right? But they shouldn't add to 2 there, right? It just doesn't make sense. Yeah, they multiply. You're gonna multiply, and you could have a whole bunch of simple, in a very complex compound machine, there could be, there could be thousands of individual machines, simple machines, working in conjunction. If you wanna find what the overall mechanical advantage is, you can take the product of all of those, right? So, in this case, we'll get in, this might be a little bit mysterious because we haven't talked about wheel and axle yet. But that's really all you would have to do is just multiply the individual mechanical advantages. Same thing would work for if you want to try to estimate what the ideal mechanical advantage for the whole thing would be, well, you could just look at the geometries of each individual machine and calculate the individual IDAs or IMAs, and then just multiply all those together, right? And that'll tell you what the bike's overall ideal mechanical advantage should be. You think a bike's going to have mechanical advantage greater than 1 or less than 1?
Greater than 1. Less than 1. If you're gonna be honest.
It's going to be less than 1, and your own experience will tell you that. How easy is it to ride up a really steep hill? Pretty easy.
Well, if you have a big gear.
If you have a mount behind.
Right, if you can,
can.
okay, so you could gear it down quite a bit, but you're never going to get down to 1-to-1. It's always going to be easier to get off the bike and just push the bike up the hill. That's always going to require less force input on your part, right?
Even if your pedals were out to the same size as the tire?
Then it would be, but they're never that way, right? On a real bike, you're always, and you can make it easier, right? If you gear way down, you can still go up pretty steep hills, right?
Being on like one of those bikes where you kind of like laying back into it.
Recumbent bike?
Yeah, I don't even know what it's called. They have like.
Recumbent bike, yeah.
Like,
You'd have to have pretty big, the pedals would have to be pretty big, or you have to go through multiple gear ratios to try to work that thing down less than 1. That's really not the purpose of a bike.
So I have
The purpose of a bike is to take an excess of force and turn it into extra speed, right? Okay. Oops. So parts of a lever. I mean, this will just be in there for your review. We'll probably not talk a lot about this. So effort arm, load arm, right? Same stuff. I mean, this is, I'm not going to go through all this. I feel like we've talked about levers plenty. Oh, real quick, here's one thing, though. So the different classes of lever, right? Class 1 means what? Fulcrum's in the middle, and that's really all you have to remember is the fulcrum is in the middle. If you remember what's in the middle, that defines the type of lever, because there's 3 things. There's input force, output force, and fulcrum, right? So fulcrum in the middle is class 1. Class 2 is
the load between the fulcrum and
good loads in the middle, okay? And then class 3.
the effort is between the fulcrum and the catapult.
Okay, good. So in the middle is going to be the input force, right? There's kind of a mnemonic device for remembering that. If you think about it this way, so class 1 is fulcrum, class 2 is resistance in the middle, and class 3 is effort in the middle. You could say FRE 1, 2, 3.
Oh,
How about that?
FRE 1, 2, 3.
There you go. Everybody.
Oh, FRE 1, 2, 3.
Okay.
Actually, every car uses the following phrase, is
Oh, really?
So good too.
That's it.
FRE 1,
All right.
2, 3.
Yeah, I'll put up the Simple Machines assignment. We'll finish this up tomorrow, and you guys can get rolling on it.
Hey, are you talking about class